Right now, we're talking about minimum spanning trees. A spanning tree is when we take our graph and unlike a circuit like we've been talking about, it doesn't loop around and start and end at the same spot. Really, we're just going to take a bunch of edges and it's going to look like, well, a tree. And the goal is to get it to cost as little as possible while still hitting all the vertices. That's why we're doing this with Hamiltonian circuits, because just it'll still be with the vertices. So a tree is a part of a graph that does not contain a circuit, doesn't contain a circuit. We'll see examples of this in a minute. A spanning tree is one that contains every vertex. Still no circuit though. So we're going to highlight edges. So for example, if I gave you this figure, and I said these are our vertices, a tree would look something like this. We've connected edges, and yeah, that's about it. We've connected edges, there's no break, but it doesn't form a circuit. A spanning tree might look something like this. Same idea. Notice all the edges that I picked all come together to be one piece, but there's no circuits involved here. We never have a closed loop, but I do hit all of the vertices. Kruskal's algorithm, that's just a way to get the minimum cost spanning tree. We'll see examples of this in a minute, but essentially we work our way from the smallest edge to the largest edge and until we hit all of our vertices. The big thing again is we cannot form a circuit. If we make a circuit, we have to skip over that edge, go to the next one. Yeah. So I'll show you an example of Kruskal's algorithm in just a minute here. But first, let's just talk about these pictures. This is obviously nothing. None of our edges are highlighted. I'm going to jump around here. D, that's a circuit because it's a closed loop. E is nothing. It kind of looks like a tree, but the problem is it's disconnected. If it's not connected, it can't be a tree. C is a tree. We run along edges. It's connected as one piece, but it doesn't form a circuit. B is really what we're after. This is a spanning tree. And the reason it's a spanning tree is because, like C, it's connected, but it hits all the vertices and still makes no circuit. So some real world. Sorry, folks. Give me a second here. So here's some real world examples for you. Airline routes would be a good example of why we'd use a spanning tree. Same thing with an electric grid. We'll see an example of that in a second. Or maybe internet providers. Kruskal's algorithm for strategy. Let's actually do an example first, because I think once you see an example, then the algorithm makes a lot more sense. So here's the situation. I have a TV company here at point A, and the goal is to get TV service to all of these places as quickly and cheaply as possible. So that just means they have to be connected to A. I can go from A, and it says we're trying to get from A to C, for example. I can go A to D to C. Or I could have done A to B to C, right? And so really what this means is we don't have to go directly from A to C in order to get cable to C, or to get cable television to point C. We just need to go from one vertex. We have to get from A to C. It does not have to be a direct path or a direct route. It also doesn't have to create a circuit because we don't have to send the TV signal back to A. So here's how this works. We're going to start by using the minimum cost edge. In this case, it's ED. Then we're going to start by using the second minimum cost, which is right here, AD. And that is 0.6. Then the third one is this guy here, AE, but we should notice something already. This is a circuit. We sectioned off this whole thing. We don't want circuits. So we have to reject this guy. The next smallest is AB. Oh. So we have AB here. So that's our next smallest of 0.7. And our next smallest is 0.75 at DC. And so what I should see right now is that even though I don't have a circuit, and it may not be the most direct route from point A, I could get anywhere. I could get to B. I could get to D. I can go through point D to get to C, or I could go through point D to get to E. All of my edges are connected. Even if it's not in the most efficient route, all of my edges are connected. So let's draw the tree just down here. It'll look something like this. Where we had A, B, C, D, E. ED was 0.5. AD was 0.6. AB was 0.7 and DC was 0.75. So that's how we created our tree. All the vertices are connected, but no circuits. If I add these up, they add up to 2.55. It says this is the cost in hundreds of thousands of dollars. So 2.55 times 100,000, we get 2,550,000. That's it, 2,550,000. So what will the total cost be? $2,550,000 to create this internet company's situation here where they could get internet to everybody. So let's talk about the strategy for Kruskal's algorithm. Not worried about hitting every edge. Notice in the last problem, we did not use every edge. However, we did need to hit all the vertices. So that was important to make sure our tree hits every single vertex. Must be connected. We saw that after we drew it separately. This is all one piece. There's not two separate pieces here. And finally, no circuits. Again, I keep saying it. It's a big deal. No circuits in trees. And again, the idea is just start at the smallest and work your way up to the biggest until you meet all of these guidelines. Now, this tree theorem here, a little bit of a trick for you. However many vertices I have, it will take me one less edge. So in the last picture, we used 5 vertices. There are 5 vertices, A, B, C, D, E. So my tree, subtract 1, should use 4 edges. Did it? Yep. 1, 2, 3, 4. So that's our way to know right off the bat, how many edges should I be using in my tree? It's always 1 less than the number of vertices. You'll notice you need to draw out the tree every time. This is not like a circuit where if I said, well, I went A, D, E, B, C, A, I could follow your path. In trees, I need you to actually draw it because there's no way for you to just list out points in order for me to know which path you chose. Example 3 here, find the minimum cost spanning tree of this graph. So as we said, start with the lowest. I see a lowest from A to B and from D to F. Both of those are 1. Work our way up. The next lowest is from C, and then around this section here, those are both 2. Sorry, that's point D. Are we done yet? Not quite, because point E has not gotten involved into the graph yet. So we got to figure out a way to get point E in. And so the lowest cost of our next edge is this 3 right here and this 3 right here. What's wrong with the second one I drew? This one right here? Because it creates this circuit. Don't want a circuit, which means I need to take this guy and not use him. So the only ones I am using are that section. So let's draw the graph over here. This was A, B, F, D, C, and E. And the weights were 1, 2, 1, 3, 2. And so ultimately that adds up to, let's see, 3, 4, 5, 6, 7, 8, 9. We have a weight of 9. And again, did it follow our rule? In this picture, we use 6 vertices. Did my final picture use 5 edges? I have AB, BF, DF, ED, and CD. Yep, we used 5 edges to make this tree. 1 less than the number of vertices. Example 4. Here's another real life example. We have a power company at A, and we want to deliver power to all the buildings. That's all of the vertices. And we want to find the minimum cost way to do that. So we'll start with our smallest. Oh, sorry, that's a 7. I thought it was a 1 for a second. Smallest is over here at EG. Second smallest is here at DF. Then DE, we're still good. We haven't made a circuit yet. Then DB, still good. Haven't made a circuit yet. And working our way up with the 6s, I see 3 of them. There's 1 there, 1 there, and 1 there. And at this point, we should notice all of our vertices. We hit all of them. So if I'm the power company at A, I could send out power to wherever I want. I could get it to D, and then from D, I could go to B, E, or F. If I want, I could get power there. I could go from A to D to E to G to H. So the power is connected there. So to draw the tree separately, we have A, B, E, 6, 5, 4. And then we have F to C. That was 3, that was 6. E to G to H. That was 2, that was 6. Ultimately, this adds up to 32. So what does this mean in the real world context of the problem? It says it would cost the power company $32,000 to deliver power to these new buildings, because it says this wire is in thousands of dollars. So that is how we use minimum cost spanning trees.